everyone, and welcome to the 3 years of romaine lettuce results under photoluminescent greenhouse films in sunny Santa Fe webinar, presented by UbiGro. This discussion will explore how an academic collaboration using UbiGro luminescent films led to a 14% yield increase in romaine lettuce through advanced spectral optimization and controlled growth trials. I'm Hillary Nguyen, the Custom Content Manager for Meister Media Worldwide, publisher of Greenhouse Grower and CE Ag World, and I'll be moderating this webinar. I'd like to go ahead and introduce our speaker, Dr. Damon Hebert, the Senior Director of Agriculture R&D for UbiQD, Inc. Damon has a background in solar materials and controlled environment cultivation. He has been with the company for more than 7 years and has overseen 60-plus commercial and academic deployments. He's an advocate for the use of advanced materials to further the industry's push towards sustainable farming practices. He was formerly co-founder and head of cultivation operations of a vertically integrated agriculture company featuring retail, cultivation, and distribution operations. At this point, I will turn the webinar over to our speaker. Damon, welcome.
Hey, thanks, Hillary. Hi, folks. Thanks for joining us today. Like Hillary mentioned, my name is Damon Hebert. I'm the Director of Agriculture R&D at UbiQD, Inc., makers of UbiGro. And we're an advanced materials company located in Los Alamos, New Mexico. You may know it from the Oppenheimer films. Today I'll be walking you through the story of how and why we've joined together nanomaterials and controlled environment agriculture. It's sort of an interesting marriage there. And then I'll be covering a fairly extensive 3-year-long student-led trial over romaine lettuce at the Santa Fe Community College, which is just about 30 minutes from our headquarters. We've worked with students and teachers there for over 8 years, and this project really represents sort of the culmination of several students' work. So my role here is to summarize that work and put it into a broader context. Okay, let's get started. So controlled environment agriculture, what's sort of the motivation behind it? Well, we know that greenhouse cultivation's been getting more and more popular because of food security and land use efficiency and water use efficiency become more important when folks choose their cultivation methods. Greenhouses, of course, allow the control over growth conditions, but also make use of our one free resource. Of course, that's sunlight. Greenhouses can produce 20 to 50 times more yield per acre than conventional field agriculture while using only 10% as much water. So we've got fires and droughts impacting farming across the globe, but greenhouses represent sort of a hedge against climate change. Greenhouses are able to produce crops year-round. They supplement conventional agriculture, and they're able to provide local crop production without excess transportation costs. So growers are finding that greenhouse cultivation offers the best combination of low cost and high quality due to the free sunlight rather than using electrical lights. And thanks to the environmental control provided by greenhouses, we can get that high quality. A lot of aspects to greenhouse cultivation are optimized or becoming optimized, such as nutrients or pest control, harvest techniques, and light quantity. But the light quality or the color spectrum, it still remains a path for optimization. So that's kind of where we're coming in at UbiQD. So I want to talk about light quality and color here a little bit. On the left there, you see the sunlight spectrum, and the colored area is the photosynthetically active region. And on the right, you see the McCree curve, which is which has been published since the early 70s. It shows the quantum yield or the photosynthetic efficiency of different colors of light. And we know that red light is about 25% more efficient when driving photosynthesis than blue light, and about 5% more efficient than green photons. What's interesting is that sunlight contains excess blue light for most crops. Sunlight is about 20% blue and 5% UV, Well, the ideal blue content for most crops is between 4 and 12%. And we know that UV doesn't drive photosynthesis directly. So if we can come up with a technology that can shift this underutilized blue and UV light into more favorable colors, we can drive photosynthesis with the same sunlight input. So we're really tricking Mother Nature, which we do in a lot of technologies in agriculture. So also note that the prevailing artificial lighting technology for indoor crops has been to use high intensity discharge sources like high pressure sodium or ceramic metal halide lighting. And at least for HPS, that peaks in that yellow to orange region of the spectrum as well. Another interesting fact is that recent studies have indicated that far red photons, those are photons beyond 700 nanometers, 700 to 750, are equally as efficient at driving photosynthesis as long as they are supplied along with shorter wavelengths or regular PAR light. Far red photons preferentially excite photosystem 1 and allow for more efficient photosynthesis in general. So there are other effects of spectrum as well beyond just driving photosynthesis. Plant morphology is affected by light color, of course. Plants will generally stretch under high red spectrum, and in contrast will remain compact under a high blue spectrum, as seen on the left there. So really a balance is needed for the proper morphology of plants. Because red photons are abruptly absorbed in canopies and far red photons are not, the presence of far red light often triggers a shade avoidance response in plants. You can see that in the middle figure there. And this can alter plant morphology and increase stem elongation and leaf expansion. Leaf expansion is typically a route towards better radiation capture and therefore better yields. Finally, different colors of light are absorbed at different rates in canopies, but also in plant tissue. So on the right there, you can see chlorophyll fluorescence imaging of leaf cross-sections where light absorption profiles have been measured in leaves. And here we see that green light penetrates deep into plant tissue, whereas blue and red do not. Because green light is the most reflective color for plants, it also penetrates into canopies and provides a more even or balanced light distribution. So even though green light is not that photosynthetically efficient, it's important to retain green light in the spectrum for any dense canopy crop. Okay, so let's step back here and think about what options exist to efficiently control light quality or color in a greenhouse. So, of course, we have supplemental lighting that can change the solar spectrum to some degree. But, of course, we have capital expenses and operational expenses that can be limiting and can reduce the efficiency or profitability of a greenhouse. In some crops, it makes sense. Others, it doesn't. In addition, in a greenhouse, the baseline spectrum is going to be dominated by sunlight, even if you do have supplemental lighting there. So really, sunlight is the main factor there. Then you have spectrally selective or filtering technologies. Some examples would be a seasonal spray-on coating or colored netting, and those can alter the color inside of a greenhouse. Well, what they don't do is maintain a high light intensity inside of a greenhouse because a filter is blocking certain colors, absorbing colors, and letting other colors through. So you generally lose a lot of intensity through these spectrally selective options. Finally, there are organic luminescent dyes, which convert typically green light to red. That's shown in the upper right there, resulting in that magenta color. So you have down conversion of light, which can maintain a high intensity. That's great. But the removal of green light in favor of red is not ideal, like I explained. Green light is important for light diffusion and absorption. Additionally, some organic dye technologies have low lifetimes in greenhouse settings, and they have not proven to be necessarily beneficial in crop yields. So, this all kind of asks the question, how can we come up with a durable, luminescent light converting material that converts, underutilized blue and UV light to orange, red, or far red? And that's really what we've developed at UbiQD. So the underlying technology, you may have heard of them. They're called quantum dots. They're really an emerging material choice for light manipulation in all sorts of applications. We use them in solar windows, for example, at UbiQD. We use them in banknotes. We use them in traditional solar. In this case, we're using them in agriculture. So quantum dots they're tiny nanoparticles. They enable the efficient manipulation or change of color. This effect is called luminescence. They down convert short wavelengths to long wavelengths, going from blue to red. What's interesting about quantum dots is they are able to be tuned based on the size of the nanoparticle. So this makes it possible to engineer tailored color recipes for crops in the agriculture space. Or, they're also used in display technology. Samsung makes a QLED television, and that Q is for quantum dots. You can get very pure colors using quantum dots. And, we like to sort of highlight the Nobel Prize in 2023 in chemistry was awarded to doctors Ekimov, Bruce, and Bowendi for the discovery and synthesis of quantum dots. Of course, we're really excited about that around here, being a bunch of quantum dot nerds. But, what's kind of interesting about that, prior to the breakthroughs in quantum dots, tuning material properties meant that you had to change the composition of a material. Whereas with quantum dots, scientists could control the optical and electronic properties by the size instead of the chemistry of the material. And we love to brag that Dr. Bowendi in particular, is on one of our patents shown there. And he's known for developing a reproducible synthesis method in 1993 that produced high-quality, size-controlled quantum dots at scale and led to their commercial use. So we owe a lot to these three folks in the foundation of our science. Okay, so let's think about what does the conversion of sunlight actually look like. We love to show this plot because it's showing the relative difference curve. So we're subtracting sunlight from the enhanced spectrum that goes through the luminescent films. So it's a difference. And note that the films enhance the spectrum in the orange, red, and far red at the top of the curve there. And the films reduce the spectrum in the UV and blue portions. So this is really what is meant by down conversion, removing some of the UV and blue in favor of more photosynthetically efficient colors in orange and red. It's important to note that fluorescence in quantum dots is a conversion and not a filter, like I mentioned before. Filters block certain colors, and you lose total light intensity. In the case of a quantum dot, the nanoparticles are converting the light, therefore conserving as much light transmission as possible. So most growers of at least high light hungry crops will appreciate this light conservation because typically light intensity loss means a loss in yield. Okay, so let's dig into the two types of films used in our plant study at Santa Fe Community College. The first type in the top row there is a laminated interior retrofit film. It's based on a PET plastic. And this is our generation 1 film we call inner. It's engineered to be suspended underneath the existing facade in a greenhouse. If you look at our website, you'll see a lot of installations using the inner films. The second type, the second row there, is our generation 2. It's our newest generation of extruded blown film. This is based on polyethylene plastic, and it's called cover. It's engineered to be used as a direct replacement for traditional polyethylene greenhouse covers. These are often used in hoop houses or high tunnels. So the second generation cover plastic is less expensive. It's lighter weight. It comes in larger commercial sizes, large enough to cover entire greenhouses. Whereas the generation 1 comes in 4-foot wide strips and is really a proof of concept for growers so that they don't have to switch out everything, their entire cover. They can cover a section of their crop, see the difference, and then expand to larger sizes. Okay, so this is kind of a summary of the experimental setup, time periods, which quantum dot films were studied, number of harvests, and number of plants. So we studied 3 specific films, 2 colors of the generation 1, that's experiment 1 and 3. That's the 600 nanometer orange on the left and the 650 nanometer red on the right. And then in the middle, we studied our generation 2 extruded film, which is also a 600 nanometer orange. So over these 3 years, we harvested more than 1,700 plants. I say we, but really the students harvested these plants, and I'll give credit to them at the end of the talk. This is the ventilated greenhouse at Santa Fe Community College. It's a unique shared space educational greenhouse. It uses solar wrap as a greenhouse cover. Solar wrap is a high-performance UV-protected multi-layer bubble insulation film. It has high transmission, high light diffusion, and really high durability. So pretty unique shared space there that we were lucky enough to be able to use. Okay, so let's talk about the specifics of the experimental setup. Here we used a nutrient film technique system to grow coastal star romaine lettuce. Nutrient film technique, or NFT, is a hydroponic growing method where plants are grown without soil and their roots are exposed to a continuously flowing film of nutrient-rich water. This film is widely used in commercial hydroponics, small-scale systems. It's efficient. It's efficient in water use, and typically plants grow very quickly. So we're able to get quick turnarounds and many, many growth cycles in the NFT system. So 2 areas were chosen for plant growth. You have a treatment area on the left there labeled QD layer. Of course, that's where the quantum dot films are suspended, and then the control area over which an uncolored film is suspended where there are no quantum dots. So the idea here was to match the treatment and control sides in light intensity and diffusion. So really the only variable between the 2 sides is light spectrum. And you can see that glow on the left in that photo too. So yeah, we're trying to isolate that one effect spectrum and see the difference on growth. Okay, so experiment 1 is shown here. This is the 600 nanometer Gen 1 inner films. Plants were harvested at different stages of growth. I've got that listed anywhere from 39 days after seeding up to 59 days after seeding. And the idea here is to sort of evaluate the growth of the plants at different stages in their growth cycle. So we understand, where spectrum might have an impact: early stage, mid stage, late stage growth. You'll see that in all of our experiments. Experiment 2, similarly, 45 to 59 days we looked at. That's the extruded film. And then experiment 3 here, you're looking at the red film, the red laminated film. And we did from 49 to 56 days after seeding harvest. Okay, the experimental setup, just an overhead view here. There's a divider between the 2 areas to prevent light spectrum crossover, of course. And we have sensors placed within the canopy to evaluate the spectrum and the light intensity over the course of the experiment. So pretty basic setup, but it's important to keep them separate and have sensors that are essentially continuously operating. Okay, so what does the spectrum look like? In the three different experiments compared to the control spectrum. Here's an example. You have the control in blue here, and then the three different spectra in red and orange. Note the reduction in blue and increase in orange and red. This is what I'm talking about when I show the difference curves. In fact, I think on the next slide we have those difference curves. Yeah, here they are. So for the three different experiments, 1, 2, and 3, we have those difference curves. We see the increase in red and orange. On the right hand, you can see the peak is much redder. Of course, that's the 650 nanometer. And then when we break down the spectral components into 100 nanometer bins, we can see the differences in blue. You can see the blue percentage goes down. The red percentage goes up. The red to far red, which is that second to the rightmost column, is a big metric we look at. Red to blue, the rightmost. We look at that metric and see if we can boost that up. So we kind of look at a relative red boost. What relative percentage of red is increased? We had between 7 and 10% increases here. And that red to blue ratio was increased between 23 and 43% with these films. The best conversion, if we look at just the most conversion, you can see that pretty high red to blue ratio in the extruded film, the middle one. But they all had similar effects from each other. Okay, so let's dig into the plant data. The exciting part, right, guys? Okay, I want to start with experiment number 3. They're numbered in time order, but I think number 3 is a little easier to understand, so we'll just kind of start with that one. So this was the red film, 650 nanometer. So in this experiment, the students looked at over 680 plants over 38 harvests. Okay, so in the upper right of the slide, I have the DLI. So DLI is the daily light integral. That's basically we're measuring every 5 minutes during the experiment, and from these measurements, calculate DLI. It's a measure of the total power light experienced by the plants during the course of the experiment, all summed together. So we have an average daily light integral for the QD film side and the control side. You can see the difference there is about 5% less under the QD side. Despite less light, the average head of lettuce was larger under the QD spectrum. So that's pretty interesting. So when we have a experiment that's sort of imbalanced, where the DLIs are not the same, then we correct this DLI difference using a fairly common metric used by academic growers called light use efficiency. And that's how many grams of produce are grown per mole of light. So in this case, for plants harvested at day 49, that's the left plot, plants were 14% larger, and that corresponded to a 20% larger light use efficiency metric. Plants grown at day 56 on the right-hand side showed an 8.5% increase in light use efficiency. And then I've put the p-values there as well. So we looked at the statistical significance using 2 sample t-tests, assuming unequal variances in one tail. That's the statistics on this whole project. And so we had significance on the left-hand side and just barely not significant, 0.06. So we look at a 0.05 p-value or less for significance. So just barely not significant on the right, but pretty close. Okay, let's move on and look at the other growth metric we looked at in these studies was leaf length. So the students also measured the average leaf length. QD films showed longer leaves at all the stages of growth. Here you can see that, but the difference were not statistically significant. But what's interesting is we saw the difference get smaller, still positive, but smaller as plants got larger. So one hypothesis is this could be an indication that the spectrum is more important in early stage growth than later stage growth, at least for romaine lettuce. It's not a trend we've seen in other crops necessarily, but kind of interesting there. Let's see, experiment 2. Let's move on to that one. Okay, experiment 2. So this is really the largest sample spanning over 1,400 plants and 80 harvests. So a lot of data points here. In this case, for the 3 different growth stages, days 45, 52, and 59, we saw light use efficiency increases of between plus 10 and plus 16%. And all 3 numbers were statistically significant. And again, this was despite a 5% reduction in total DLI underneath the QD films. So I think a pretty impressive result over such a large sample. And you can see, biology is noisy. You guys can see that in the data here, but that's why you have to do so much sampling over such a long time period to show that significance. Looking at the leaf length in experiment 2 as well, we didn't see huge differences here. Just 3% increase for the early stage growth and about 2% for the late stage. Of course, these are such small numbers. It's no surprise they're not significant statistically, but at least positive numbers in average leaf length there. All right, moving on to experiment number 1. Here we looked at 4 different age ranges of the plants for harvest. And sort of a wider variety of results here in wet weight increases. So here we're plotting the wet weight, because in this case, we actually had a pretty close DLI difference. In fact, QD films had 2% more light. And this might be due to the fact that these experiments were performed in different seasons, and therefore the sun angle can have an impact when balancing out 2 sides of an experiment. But 2% is really low, so we're just going to plot the wet weights here instead of light use efficiency. So here you can see anywhere from 4.5% up to 28% yield increases in wet weight, depending on the age range of the plants. But for all these groups, the values, 3 of the 4 values were statistically significant, the 3 larger values. And then we, of course, looked at leaf length here as well. Here we, go back one. Yeah, there we go. Here we had small increases, 7, 8, and 7% for the early stage growth, and just 3 or 4% for the late stage growth in leaf length. But we did add some significance statistically in two of the 5 age ranges of plants there. So we actually did show some significance there. And again, all plus values. So larger leaves, more radiation capture, larger yields. Makes sense. Okay, getting towards the end, what I want to do is really kind of take all this data together, put it in one table so we can kind of digest it together. So I've listed the 3 experiments here. And then I've highlighted the results, the yield results in green that were statistically significant, white that were not, and then light green for the almost significant. And then I've done an aggregate percentage on the right there. So anywhere from 12 to 17% increases in yield. And if we kind of take all these together, and we weight them by the number of plants as well, we had a 14.0% yield performance over the 3 years and 2,700 plants. So, I think pretty convincing, given the duration and the number of plants. And if you compare this to, we've done a lot of studies with commercial growers and academic growers over the past 5 years. And this is the most extensive in terms of duration and number of harvests that we've ever done. So really love this data set. It shows how noisy biology can be, but also that we can draw conclusions from it. And what's also interesting here is that the orange layers was the extruded layer performed a little worse than the laminated layers. And we don't necessarily have a reason for that. I mean, it could be within the error bars and percentage there. But also we saw that the orange layer outperformed the red layer, which is a trend that we've seen in different studies going all the way back to 2018, our first trial with University of Arizona and NASA doing indoor lettuce. So, I don't want to take the credit for this. I really want to thank three amazing students, Michael, Lydia, and Amanda, who did all the plant work, measurements, seeding, all the way to harvest, weighing everything out. And that was all under the tutelage of their teacher, Charlie Schultz. And then I also want to shout out to my colleague, Charles Parrish, who helped me manage these trials over those 3 years. Okay, before I wrap up, I want to just kind of give a little sneak peek of what's next at UbiGro. So in November, we launched the cover product that you saw here in prototype form. We launched it commercially in November. We've only done a few installations so far. You see one in the bottom middle here, which is in Alcalde, New Mexico. Upper right here is New York State. And upper middle is an artist rendering. That's our vision of what we see. Glowing greenhouses helping the world get more produce from their one free resource, sunlight. So if anyone's interested in pilot studies working with us, we typically do offer discounts if growers are willing to share data with us. And then we can publish case studies on our website. And yeah, just check out our website if you guys want to know more. We've got a lot of different case studies. This one's up there, kind of written up briefly. Okay, the other thing that's next I'm really excited about is the UbiGro glass. So this is glass infused with quantum dots rather than plastic. Glass greenhouses are used in a lot of northern climates over really high value crops like tomatoes, peppers, cucumbers, strawberries, stuff like that. And we've just launched some prototypes with the help from U.S. Department of Agriculture, their support through an SBIR grant. We've been working with UC Davis to test this out. First trial over lettuce had a 38% yield increase. It's better than we expected. We're continuing to work with them in a phase 2 and launch some commercial trials for UbiGro glass. The big difference with glass and the challenge is that glass panels are only replaced every 20 to 25 years. So we've got to make a product where those quantum dots last for quite a long time. It's not 4 years in plastic, it's 20 to 25 years in glass. So challenge there, but something that we're really excited about. So I want to thank everybody for attending today. If you have any questions, please reach out. There's a couple email addresses there. If you want to contact me directly, feel free to email me. And yeah, we're always looking for growers who want to partner with us, do a pilot trial. I manage our pilots, so I'm the guy to talk to for that. And we'll get you outfitted here in the next few months. Thanks so much.
All right. Thanks, Damon. It looks like we've got a few questions, so we can go ahead and dive into those. How long does the exterior film last?
Yeah, thanks for the questions. Yeah, so both the inner film, which is the PET plastic, and the cover film, which is the polyethylene, are 4-year films. So 4 years, and that's pretty typical with your polyethylene. So we're trying to match or exceed typical polyethylene layers. So you don't have to change your normal behavior. So I mean, we do find some growers who change it out every 2 years. We find some growers change it out every 6. So you should just think whatever my normal polyethylene replacement cycle is, this is the same durability, because the outside layers in our cover film is the same as any other polyethylene cover. So its durability is the same.
Has any research been published in peer-reviewed journals using these glowing greenhouse films?
Yeah, I mean, we've worked with a lot of different schools. Other than Santa Fe Community College, we've published in a Nature journal, Comms Bio, with the University of Arizona on a lettuce trial. We've published in Hort Science with Texas A&M on lettuce and basil. We published recently in Materials Today Sustainability on the glass results with UC Davis over lettuce. And we've worked with other schools like Arizona State University, Windward Community College in Hawaii, Wageningen University of Research in the Netherlands, and more recently, North Dakota State University. So yeah, we've done a lot of academic work.
In what locations have the luminescent layers been tested, and in how many greenhouses?
Yeah, so I think our pilot trial numbers is about 60 right now. So that's not just customers, but folks that have done either academic or commercial trials with us and shared data. So yeah, we're about at 60, and then add on a bunch of customers on top of that. So over 100. The locations I think we were at, last I looked, was 12 different foreign countries, and I think it was 9 different U.S. states right now. So we've got quite a bit of coverage in different geographies. We've seen a little bit of a trend that we get better performance in the sunniest climates, which might make sense. I mean, every bit of sunlight we can convert is increased value. And we've had a little bit better performance in high altitude because of that UV content in high altitude. Sunlight is higher, so we can convert that into photosynthetically active radiation. So, New Mexico has done really well, of course, in sunny places like Spain, Texas, California have all done really well.
Thoughts on how weather could impact results? Hotter or colder climates, more humidity or less humidity?
Yeah, I mean, I don't think we have any data on the humidity levels being a factor. So, but like I just mentioned, it's amount of sunlight. So, you could take the how sunny your climate is, and then how long your days are. So that part's would be a factor. And then again, the altitude with a little bit more UV tends to boost. But that being said, I mean, we've tested in cloudy, not sunny places like the Netherlands and Canada, and still had positive impacts. Just the degree of that positivity wasn't as large. So the economics aren't quite as good. But typically they're still really profitable for the grower.
How long do these films last in a greenhouse?
Well, you already asked me that one, Hillary.
Did
4
I?
years.
Oh, sorry. Like popped up again.
No worries.
All right. Have you trialed this in profile or sheet extrusions, optical materials like acrylic or polycarbonate?
Yeah. So we haven't tried in at least not in commercial applications in polycarbonate or acrylic. Part of the issue, I think, and I'm not the materials manufacturing guy on our team, but I believe that the issue there is temperature. When you put quantum dots into a manufacturing process that's high temperature, then it can kill the luminescence of the dots themselves. So there's some factors to be explored there. Now, one route we're exploring is an optically clear adhesive that would attach a plastic quantum dot layer to any material. So that would probably be the route for polycarbonate or acrylic at this point.
Can these glowing films be used with supplemental lighting?
Yeah, so we have a lot of our customers, maybe half, that also use lighting to supplement. So, extending their photo period. supplementing in winter, stuff like that. And so they're using them in conjunction, using our films in conjunction with supplemental lighting. The thing to kind of ask yourself is, what percentage of my photons are artificially derived versus sunlight derived? Because UbiGro is only affecting the sunlight derived photons, of course. So if you're, really high percentage artificial for a lot of your time, then it's maybe not the best. But if you're, say, 70% sunlight derived photons versus 30 artificial, then we could have that impact. It would just be slightly mitigated versus a greenhouse where it's 100% sun and 0% artificial.
Looks like we've got one more. What is a typical payback time for these films when used over lettuce?
Yeah, so lettuce is a fairly high value crop per square meter, per square foot. Not quite as high as tomato. But for high value crops, we typically have a payback time between 1 and 2 years. So if you compare that with a 4-year lifetime, it's pretty good investment. And then, the other thing is that we're scaling up our manufacturing, so our costs have been going down. And so that is really boosting or, reducing the payback time, boosting the return on investment.
All right, we've got one more that just came in. Would fruiting crops benefit differently from vegetative crops under the films?
Yeah, that's a great question. I don't know if we've got our finger on that quite yet, but we have done a lot of testing on fruiting crops, strawberries and tomatoes being the biggest ones that we've studied. We've also done some cannabis studies. And they're all showing really good responses to the spectrum. But I think just sort of a general increase in photosynthetic rate is helping in all stages of growth. So it's getting plants to the size they need to be. It's getting, bigger leaves, better radiation capture. And that all will feed into the fruiting portion. So it's not that we're driving faster fruiting or anything like that. The spectrum is not. The spectrum is a change, but it's not such a huge change that your plants are going to react sort of negatively or unpredictably. But yeah, encourage you to contact us and start with a trial and see how it affects your greenhouse.
All right, one more just came in as well. Do weather events like hailstorms damage the product? Would it need replacement?
Yeah, so it's no different from other polyethylene films as far as the cover. So the cover, of course, that's a question for that. The inner, of course, is protected because it's suspended underneath the existing facade. So if you had a hailstorm that would damage regular polyethylene, then yes. But I think mostly polyethylene's pretty good at not being damaged in hail. You pull it really tight and hail is just going to bounce off as long as it's really tight. But, I'll say it's not my biggest area of expertise.
Okay, that does look like it is the last question. So thank you all for attending today's webinar. A special thank you to UbiGro for presenting it and to our speaker, Damon, for sharing valuable insights into how this collaborative study demonstrated the power of spectral manipulation with UbiGro films to significantly enhance leafy green production. If you want to watch the webinar on demand or revisit certain parts, it will be archived and available at the same link you used to access it today. You will also receive an email reminder of the archive with the link tomorrow. Thank you again for joining us. This concludes the webinar.
Thanks.